Hey everyone. So today I'm going to be doing an online lecture for analysis of variance. That way, if in the future we have to do any hybrid classes, you can look at these notes. So analysis of variance, what is that? Also known as ANOVA. So last week we were talking about this new thing called a t-test. And the t-test is a technique that we use for calculating if there's a significant difference or a vast or huge difference between two groups in terms of their mean on some variable. We used the example of liberals versus conservatives. Right? Those are our two groups that we're comparing, and we're looking at their permissiveness scores. So are liberals or conservatives more permissive in their child rearing practices? And we can use a t-test to see how far that difference between liberals and conservatives in their means, how far that difference is. But that was one example. We had several other examples looking at t-tests, but many times in social research, many of the questions that we have can't be boiled down into only two groups, right? We might be concerned with things like racial categories. There are several racial categories. I don't know if many of you have seen the census or have filled out the census before, but there are several racial categories. So if we wanted to do a t-test based on the restrictions of a t-test, we would only be able to look at black versus white, or black versus Asian, or white versus Asian, only two groups. But these kinds of research questions are variables that have multiple categories. We can't adequately use a t-test for it, right? What if we wanted to see how racial categories differ in terms of their mean incomes? Do whites have higher mean incomes than blacks, or is there a difference in mean income between blacks and whites and Asians and everybody else? Right? We need some more sophisticated technique to answer those kinds of questions. Now, as you know, we did last week, we looked at this thing called a t-test, or looking at t-ratios. And we could, with these several categories, let's say we had 5 racial categories, what we could do is compare one versus the second, the first versus the third, the first versus the fourth, so on and so forth. Right? Let's say we had black, white, and other. We would compare incomes for black versus white, see if there's a mean difference between blacks and whites, then compare blacks to everybody else to see if there's a mean difference between incomes from black people versus everybody else, and then we would next compare whites to everybody else. Is there a mean difference in income? But we remember this issue of alpha, or selecting an alpha beforehand, right? And alpha is usually stuck at 0.05. What that means is we're willing to accept a 5% chance that we're going to be wrong. That also means that we're only willing to accept a 5% chance that the null would be right in our case. However, with each t-test that we run, there's that same alpha level. So if we run a t-test between incomes, mean difference on incomes between blacks versus whites, that has an alpha level of 0.05. And then we run the next t-test, blacks versus everybody else. That also has an alpha of 0.05. And then whites versus everybody else. That also has an alpha level of 0.05. So every time we run a t-test, we're saying we're only willing to accept a 5% chance of being wrong. But if we run it 3 times, that's 3 t-tests. We're essentially saying for every time we run it, we're willing to be 5% wrong. So we have to multiply that alpha level by the number of t-tests that we run. So essentially, instead of just having a 5% chance of being wrong, or a 5% chance of the null hypothesis being true, we end up with a 15% chance of the null hypothesis being true. Another way of saying that is we're only 85% confident in the findings that we have. And that's not something we want. We want to be 95% confident. That's our cutoff. We want to be 95% confident. So, for each t-test that we run between blacks and whites, blacks and others, and then whites and others, if we find that we reject the null hypothesis in each of those, we could be incorrectly rejecting the null, because essentially we have a 15% chance of rejecting the null instead of a 5% chance of rejecting the null. So we could run and keep finding, we could find 3 significant relationships when there might not be significant relationships. So we need an overall test to correct for that alpha level. We need a test that holds that type 1 error rate or that alpha level at 0.05. So it says no matter how many comparisons we run, if there are 3 groups, 4 groups, 15 groups, and we want to compare them all, we don't have to run 1,000 t-tests. We just run one test that will control the alpha level and keep it at a 0.05. And that test is called the analysis of variance, or ANOVA, or ANOVA, analysis of variance. So ANOVA is an inferential statistical technique, like the t-test is, inferential technique to test for significant relationships between 2 variables. So much like the t-test, the ANOVA comes directly out of the t-test. It says our independent variable is a nominal variable with more than 2 groups. Okay, that's the difference. For a t-test, we're only comparing 2 groups. For ANOVA, we have that same nominal variable, but it's more than 2 groups. So 3 or more groups that we're comparing. And much like the t-test, it also looks for differences in means between these groups. So if we're looking at mean income and the differences in mean income by racial category, we're looking at how much difference is there in mean incomes between blacks and whites, whites and others, and blacks and others. So we're still looking for differences in means. So our independent variable, again, like the t-test, is nominal, but our dependent variable is interval ratio because we're calculating means. The interesting thing here is that ANOVA allows us to calculate both differences between these groups, or between the samples, as well as within each group. So what that means is that we're looking at how blacks differ from whites, blacks differ from others, and whites differ from others, but we're also incorporating a measure that allows us to look at within the black group, how does each person's score differ from the overall mean of the black group? Within the white group, how much does each person's score differ within, for all whites, how much does each person's score differ from the white group? And then same for others, right? So is there a lot of variability or a lot of deviation going on within each group? Kind of that idea that we had last week or a couple of weeks ago where I showed a gerontologist is testing a new method for recall for an old folks home or a nursing home, and she uses method A, and all these scores in method A are really high, but they're all centered around the low 80s. And then method B, which is the old method, they're all in the high 70s. All scores are in the high 70s. So there's very little variability within each group. But then there's a huge variability between the groups, right? 77 was the mean for method B, 82 was the mean for method A. But within each group, all the scores were pretty close to one another. So this ANOVA does that same thing. It allows us to look at what's going on within each group and see if that's a lot of variability or a little bit of variability, and then compare to overall how much variability is going on, how much difference there is between all the groups. So this is kind of an example. So it calculates variation across all groups, right? And it breaks it down into 2 components. We have, in this top figure here, we have x1, which is the raw score of person 1, and they compare that to the mean. So if we look at this lower class curve on this first figure, we see the mean of lower class, and we see that person 1, or x sub 1, is lower than the mean of group 1. Same for group 2, working class. We see that the mean for group 2 for working class is higher than the raw score of person 2 within that group. So we see the difference here is that we have x sub 1 and then x bar sub 1, where x bar is the mean for that group, and then we have x sub whatever number, and that's the raw score for each person. We also see that the means for each curve, for lower class compared to working class, compared to middle class, compared to upper class, the means, or the center point between within those curves, the means increase by the class level, right? The lower class mean is lower than everybody else. Next comes working class's mean, next comes middle class's mean, then upper class's mean. So in that curve, we're looking at every person's score within each group. It's not comparing person 1 to the mean of working class. Person 1 is in lower class, so it's comparing that person to the mean of lower class. Next, so that's the first part where we break it down into variation within groups. So it looks at the deviation of everybody's raw score from their own group mean. And then we look at variation between groups. Variation between groups is how much variation or how much deviation, how much difference is there between each group themselves. So it looks at the mean of group 1, it compares that to mean of group 2, to mean of group 3, to mean of group 4. Right? So it just says, is there huge variability in the differences between all these means? And is that more than what's going on within each group? The logic of ANOVA really is trying to specify, do these curves, right? Because we're assuming that there's an underlying normal curve for every group. The logic of ANOVA says, if these groups are truly different from one another, there should be no overlap. So lower class should not overlap with working class, should not overlap with middle class, should not overlap with upper class, right? There should be a significant or huge spread between these groups. Or there should be very minimal spread between these groups, right? So right now it looks like these curves between these groups are overlapping, but it's also looking like the overlap is in the tails, with the exception of working class compared to middle class. So when we look back at the t-test does the same exact thing. The t-test says, well, we're going to look at variation between these two groups. So it calculates group 1 and group 2. So it does group 1 differ from group 2? And that's what we find in the numerator of the t-test calculation. And then last week I showed you how to calculate the standard deviation. And the standard deviation takes into account the number of cases involved in each group, as well as the standard deviation for each group. So what this does for us is it calculates a standard deviation that's going on average, within each group. There's one standard deviation calculation that accounts for the variation going on within each group. So how much on average are the scores within each group close to the mean or far from the mean? So the t-test is doing the same thing that ANOVA is doing. We just calculate it differently. So t-test has this thing called a t-ratio or a t-score. So we have z-scores, then we recalculate the standard deviation in the denominator and we come up with a t-score or a t-ratio. And then now we have ANOVA that's looking at more than two groups. So now in ANOVA we have this new number called an f-ratio. And in the numerator, much like the t-test, the numerator is the variation between groups, denominator is variation within groups. So this f-ratio is what we end up with, and it indicates the size of the difference between groups relative to the size of the variation within groups. So the numerator, if we have higher variation between groups than we do within groups, that means that the numerator is going to be higher than the denominator, right? So think of it this way. Let's say we had a fake measure of variation between groups, and that's going to be 100. And then the amount of variation within groups was 10. Okay, so numerator is between groups, that's 100. denominators within groups, that's 10. So 100 over 10 is 10. So we're going to have an F ratio of 10. Now, let's think of this. If we had less variation between groups, let's say the variation between groups, the numerator, was equal to the variation within groups. We'd have a numerator of 100, a denominator of 100. 100 over 100 equals 1. So an F ratio of 1 would indicate that there's the same amount of variation going on between groups as it is within groups. So that means that there's a high amount of overlap between each group, that they're not really that different. So on the flip side, if we have our first example, a numerator of 100, denominator of 10, we have an F ratio of 10, that means that there's a lot going on between groups. So group 1 differs from group 2 drastically, and that differs from group 3 drastically. So a larger F would indicate that there's more variation between groups. That means that there's more difference between these group means. And that's what we're trying to get at with an F ratio and the t-test. We're trying to look at differences between groups. Is there a mean difference between these groups? So we want our numerator, if we're going to find a significant difference between these groups, we want our numerator to be high and much higher than the denominator. So again, I said this. If there were no group differences, the relationship between the groups would be the same, right? The variation between groups would equal the variation within groups. That means our F ratio would be 1. A larger F means that there's a greater likelihood of rejecting the null hypothesis. So what we do is we try to find if there's larger variance between groups relative to variance within the groups. And if we find that, we know that the dependent variable varies significantly or differs significantly across the different groups of our independent variable. So, for example, we had racial categories. Let's say we had 5 racial categories, and then we had income as our dependent variable. And we're looking at differences in mean income across these groups. So if we find that the variance between groups is much larger than the variance within groups, that means we have 1, we have a high F value. That means 2, we're going to likely reject the null hypothesis if it's really high based on our distribution. But that also means that this last part, the dependent variable, so income, differs significantly across the different groups. So that means that blacks have different mean incomes than whites, have different mean incomes than others, then have different mean incomes than Asians, and so on and so forth. This means that the groups have significantly different means. Here are the null and research hypotheses. We know that null hypothesis is this first one, H naught or H sub 0. It means that all groups have the same mean, or all group means are equal. So group 1, the mean of group 1 in the population is equal to the mean of group 2 in the population, is equal to the mean of group 3 in the population, is equal to the mean of group 4 in the population, so on and so forth. The research hypothesis says the opposite. It says the group means are not equal. So mean of group 1 does not equal the mean of group 2, does not equal the mean of group 3, does not equal to the mean of group 4. So if we reject the null hypothesis, that just means that there's a significant difference between these group means. Really what it means is that at least one of these group means is significantly different than the others. There's no real way of determining which group is really pulling the difference. So we could have a situation, for example, we could have a situation where blacks, whites, and Asians have really low mean incomes, and then we have this other category, our fourth group, that has really high incomes. And then we look at this difference, which says, whoa, there's a huge difference between these groups. And what's really happening is that others are significantly different from everybody else. So what the F-test really does is it says that if we find a huge difference between the groups, it just says that at least one of these groups is hugely different than everybody else. It could be that two groups are different than everybody else, but what it's showing us is that there's at least one group that's different. And we can talk about this in class at a later date, but there are tests that you can do called post hoc tests that will allow us to see which group is holding the relationship. You can also just look at the means. If blacks, whites, and Asians have really close means, and then we look at others and they have a high mean income, we can say, well, that's probably the group that's creating this significant difference between the groups. It's important to highlight some of the assumptions that go along with any inferential test. The assumptions of ANOVA are that we have independent random samples. The dependent variable is interval ratio. The independent variable has more than two groups, and that the population is normally distributed. So independent random samples and the population is normally distributed, so the first and last points are usually kind of assumed, right? But what's really important here is that the dependent is interval ratio and the independent variable has more than two groups. There are several kinds of ANOVA that we could use, but the main type of ANOVA that we use in this class is called the one-way ANOVA. And the one-way ANOVA is called the one-way ANOVA because it has one dependent variable and one independent variable. We have other kinds called repeated measures ANOVA, or repeated measures ANOVA, which is measuring the same people over several periods of time. That might remind you of a paired samples t-test. Same thing. T-test, paired samples t-test would just be measuring the same people at 2 time points. Repeated measures ANOVA would measure them at 3 or more time points. And you see how that 3 or more comes back into play? We have factorial ANOVA, we have Mankova, all kinds of ANOVAs, but in this class we focus mainly on the one-way ANOVA, so one independent, one dependent variable. So when we compute this F ratio, it's important to know what all the parts are. We have to compute the variation between the groups and the variation within each group. But first, we have to calculate this thing called the sum of squares, and that's the sum of the squared deviations from the mean. Burl, wow, deviations from the mean. Squared deviations from the mean, what does that sound like? Oh yes, that sounds like when we were calculating standard deviation. When we were calculating standard deviation, we know that a deviation score by itself, if we sum them all up, that deviation score would sum to 0, right? One person's raw score from the mean, another person's raw score from the mean, we add all of those numbers up, you're going to have some positive, some negative, they're going to cancel out and equal 0. So, what we do is we do the sum of the squared deviations from the mean. Right? So here's an example of how we calculate some of that variation. We have this arrow that's pointing from group 1, that number 7, down to the mean of that group, which is 6. So that's called our within deviation. We can see that 7, that person's score of 7 within group 1, is 1 value away from the mean. So they are 1 score, or 1 point above the mean. Okay. Then we compare this, what we call between deviation, which is the mean of group 1, which is 6, to the mean of all the groups. So we have mean of group 2, which is 1. We have mean of group 3, which is 2, right? So we have mean of group 1 is 6 compared to the total mean, which is 3. So a good rule of thumb here is that within deviation is 1, between deviation is 3. The total deviation that's going on in this whole group, all of these groups, is 4. Right? And that's the addition of within deviation plus between deviation. So we have a total sum of squares that's calculated this way. Everybody's raw score minus the mean of all the groups squared. X bar subtotal is also known as the grand mean. And what that is, it's the mean of all the group means. So mean of group 1, mean of group 2, mean of group 3, and the mean of all those means is called the mean total. So we take everybody's raw score, subtract it from the grand mean. And that gives us the sum of squares total. The sum of the squared deviations from the total mean is that. But a good thing to know is that we have this total sum of squares can be calculated this way as well. It's the sum of the squares between plus the sum of the squares within. And I apologize for that SS between. But it's just the sum of the squares between each group plus the sum of the squared deviations within each group. But we don't know those parts yet. So the between group sum of squares, or sum of squares between, is calculated this way. You take the mean difference between all groups. We take the mean of each group, so mean of group 1 minus the grand mean, or the total mean, squared. And we say, how many people are in group 1? We multiply that by n of the group, or the total number of people in each group. Then we do it for group 2. The number of people in group 2 times the mean of group 2 minus the mean of all the means squared. And then we do that for group 3 as well. Next, we have the within group sum of squares. So the squared sum of the squared deviations within each group. So this makes a lot of sense. We're looking at variation within groups, so we're saying we're going to take everybody's raw score and look at how that differs from the group mean. So we say the sum of one person in group 1 minus their group mean squared plus person 2 in group 2, 3 in group 3, or group 1, and the fourth person in group 1, so on and so forth. Then we calculate that same thing for group 2. All the people minus the group mean in group 2. Then group 3 we do the same thing. All the people, the raw scores of everybody in group 3 minus the mean of group 3. So to calculate the sum of squares within, it's the same thing as our calculation of the sum of squares total. It's the sum of squares total minus the sum of squares between. However, we need a pure version of this measure. And what I mean by pure is we've been squaring a lot, right? We keep squaring because anytime we calculate a deviation from a mean, we're just getting zeros. So we have to square it, right? By squaring it, we just keep getting larger and larger and larger numbers. And we don't end up square rooting it back again. So what we're saying is that this sum of squares measure becomes larger as 1, variation increases, and 2, if we have huge sample sizes. Right? So we're just adding a bunch of scores. If there are 2 people in each group, we can calculate how much they're varying. But if we have 3 people, that's another squared number that we're adding. We have 4 people in each group, that's another squared number we're adding. Right? If we have 100 people in each group, that's 100 numbers that we're calculating differences for and then squaring. So the larger the number of people in each group, the higher and higher this sum of squares number is. So because the sum of squares is just getting ridiculously large, we need a more pure measure that accounts for the number of scores that are included. And we do this by, oh yeah, degrees of freedom. We remember talking about degrees of freedom before, right? We had degrees of freedom for standard deviation, which was n minus 1. We have degrees of freedom for the t-test, which is n of group 1 plus n of group 2 minus 2, right? So what we need to do is say we're going to calculate the sum of squares, but then divide by the total number of cases, but an adjusted or a correction factor for that number of cases, which is called the degrees of freedom. So we're going to divide the sum of squares by the degrees of freedom. So we calculate two kinds of degrees of freedom, which lead to two types of new measures. We have a sum of squares between, sum of squares within, and sum of squares total. But really we're concerned with between over total. So we need a new measure that's more pure. Instead of just between over total, sum of squares between over sum of squares total, we're going to do mean square between versus mean square total. So to calculate the mean square between, we say the sum of squares between divided by the df, degrees of freedom between. Same for mean square within. We do sum of squares within divided by degrees of freedom within. And we'll see that down here there are two types of degrees of freedom. Degrees of freedom between says, what is the number of groups that you're calculating? If there are 15 groups, we're going to say we need to account for those groups, the number of those groups. So degrees of freedom between is k, where k is the number of groups, minus 1. So if we had 15 groups, degrees of freedom between would be 14. In our past example, we've been using 3 groups. So black, white, and other. So if we had 3 groups, k would be 3, so degrees of freedom between would be 3 minus 1, which is 2. So we'd say the sum of squares between over 2. Then we have degrees of freedom within. Now I didn't come up with these calculations. These are long-standing statisticians from way long ago who came up with these calculations. And they hold true ever so today. So now we have this thing called degrees of freedom within, which is a calculation of how many people are within each group. So what it does is it says what is the total number of people across all the groups minus the number of groups that exist. Right? So we're counting for the number of groups. So here, let's say we had 10 people in each group, so across 3 groups, so that's 10 plus 10 plus 10 is 30, that's the total n, minus 3. So that's 30 minus 3 is 27. So degrees of freedom between is 3 minus 1 is 2. Degrees of freedom within is 30 minus 3 is 27. So we're dividing sum of squares within by 27. Now to calculate these statistics, much like we did with the t-test, we calculated variation between over variation within. Now we're doing that same thing to calculate an F statistic for ANOVA. And it's the ratio of the mean square between over the mean square within. So as soon as we go through all these steps of calculating sum of squares total or sum of squares between and sum of squares within, then we can calculate mean square between, mean square within, and then next calculate that F ratio. If we want to find a significant relationship, we want to find a huge or very large F ratio, meaning that the between mean square is much larger than the within mean square. Another way of saying is that the between variation is much larger than the within variation. So the F ratio is something, this F value represents the ratio of between group variance over within group variance. So much like we had the T value or T ratio obtained, and we compared in the back of the book to the F critical, or to the T critical, we do the same thing for the F ratio. We have F obtained, which is something that we calculated on our own, and then we have the F critical, which is based on the alpha level that we want, and it's in the back of the book. So let's assume here that we have 21 people. So n equals 21. And this is the total number of people that exist across our groups. We have 4 groups here. So we have a group of 5, a group of 5, a group of 5, and a group of 6. We go through this long-standing calculation, and we're looking at how education levels differ by sex and race. So in this example, we're looking at men versus women, but also black versus white. So now we have black women, black men, white men, white women. Right? So we have 4 groups. And across those groups we have 5, 5, 5, and 6 people in each group. Across all the groups. We go through this hand calculation and we see that the sum of squares between the groups is 31. The sum of squares within each group is 45. That means there's a lot of variation going on within groups, but not that much variation going on between these groups. Right? But remember, this measure is outlandish because we're squaring all of these numbers. Right. Then we calculate degrees of freedom between, which is 3. So 4 is the number of groups, minus 1 is 3. And then n is 21 minus 4 is the number of groups, is 17. So now we come up with a calculation for mean square. We have to calculate that because these sum of squares numbers are too ridiculous. They don't make much sense because we squared them. So we come up with a calculation of mean square between over mean square error. For us, we find that mean square between is 10.6, so it's 31.83 divided by 3, compared to mean square within is 45.33 divided by 17. So there's much more variation going on between groups than there is going on within groups. So to calculate our F ratio, we say mean square between over mean square within, which is 3.97. Basically, we've just gone through a way to calculate our F ratio obtained. So this is from the data that we have. This is the F ratio of variation between all of these racial and sex categories on education, and as well as divided by the variation within each group. So the next step is to figure out, is that a huge F ratio or a small F ratio? How do we figure that out? Well, we have to compare it to an F obtained or an F critical value in the back of the book, just like we did with the t-test. So we can determine the significance of our F. And how do we do that? Well, we need to know, one, much like we did with our t-test, we needed to know the degrees of freedom. But here we have 2 degrees of freedom. We have degrees of freedom between as well as degrees of freedom within. So what we need to do is take both of those degrees of freedom at our alpha level and see what the critical F value is. And just like we did with the t-test, we want our F critical to be lower than our F obtained. Another way of saying that is we want our F obtained to be much larger than, or just any amount larger than our F critical. Our obtained needs to be larger than our critical. If it is, it means that our relationship is significant. It means that there is a significant difference between the groups in terms of the dependent variable. There's a significant difference between sex and race groups on their education levels. All right, so we have this calculated or obtained 3.97 F value with 3 degrees of freedom between and 3 and 17 degrees of freedom within. So we have to go to the back of the book to figure that out. Let's figure out where this is. Our F table should be called Appendix F. Let's see where it is. Appendix Z. Appendix R. So we have our critical F table, which is on page 672 in the old book. It's Appendix F. So we have several tables. Table 1 is alpha of 0.05, which is exactly what we've always been using. And then appendix, or table 2 is 0.025, and then table 3 is 0.01. So we're just going to stick with this 0.05 table, so table 1. So what we do is we find, so not paying attention to these notes in the slides here, but we'll go to page 672, and on this table we'll see the columns are the degrees of freedom in the numerator. The rows are the degrees of freedom in the denominator. So we've already seen that we have a degrees of freedom between, that is 3, degrees of freedom within, that is 17, right? So numerator is between. Remember, we're always looking at between divided by within. So the numerator is between. So we have between is 3. So we go over to column 3, and then we go down to row 17, because that's how much degrees of freedom are within. Column 17. So at column 3, row 17, our critical F value is 3.2. So we see that our critical F value is 3.2. We say that if our F that we calculated is larger than this F in the table, we know our obtained F is significant. And we know that because this table reports the level that we have to reach to be significant. And this table says that we're at the 0.05 level. So we know that if our F is larger than 3.2, we know that it's significant at least at the 0.05 level, because this is table alpha equals 0.05. So we look at the back of the book and we see, using this table with 3 degrees of freedom in between, 17 degrees of freedom within, we have a calculated, or a critical level, critical F value of 3.2. Our obtained F value is 3.97. So now we know that our F obtained is larger, much larger than 3.2. Now we can use that to say that our critical F is larger and that it must be significant at least at the 0.05 level. This means that if it's significant at the 0.05 level, there's a less than 5% chance that the null hypothesis is true. Remember the null hypothesis in this case. The null hypothesis says that all the means for every group, all 4 of these groups, are the same. What we've just found is that the means are not the same. The means between these groups differ so much that we ended up with a large F value. So that the null hypothesis here is less than 5% true, meaning that it's more than 95% true that the research hypothesis could be true. More than 95% chance that the research hypothesis could be true. So we have to report this. And by reporting, we're just saying this is how we write it out. When you write it out, you list the test used, whether or not you reject the null hypothesis, the variables in the analysis, as well as the degrees of freedom and calculated value and the p-value. So here we say, using a one-way ANOVA, that's the test we used, I reject the null hypothesis that there is no mean difference in years of education across these groups. And the groups are white males, white females, black females, by gender or race. And then, comma, we report this line up here, F, and then parentheses, we say degrees of freedom between, comma, degrees of freedom within, in those parentheses, and then we equal the calculated or obtained F value, and then comma, whatever the p-value is. And right now we don't have a full-on p-value because we haven't hand calculated everything, but we know that it's less than 0.05, less than a 5% chance that the null hypothesis is true in this case. So we say F, and in parentheses 3, comma 17, equals 3.97, which is our calculated F value, and then P is less than 0.05. And this is what it looks like. you'll notice that the F curves are slightly different than the Z normal distribution and the T ratio or T distribution. The F curves are only positive. Why is that? Well, we squared all the numbers and then created a ratio out of them. We didn't square root them or turn them back into original numbers, so they're all positive numbers. So here is the critical F value of 3.2. Our obtained F value is 3.97, so it falls within that, what we call rejection region. So we reject the null hypothesis in this case. And this is another example of how to calculate the F value. So I'm going to have you do this in class when we meet next. Alright, that's it for this lecture, and we will meet next week to talk.